Hi, I'd like to talk about the physical properties of elastic collisions. Now, elastic collisions are the exact opposite of what we call inelastic collisions. Inelastic collisions are collisions where the kinetic energy changes. Now, for an explosion, potential energy in the form of internal chemical potential gets turned into kinetic energy. For perfectly inelastic collisions where objects collide and stick together, then kinetic energy has to change through that energetic process of having the objects stick together. Even sometimes when an object bounces, there's a change in kinetic energy. Well, whenever we have elastic collisions, they are perfectly bouncy. So not only can we conserve the momentum, we also conserve the total kinetic energy before the collision and after the collision. So for any conservation of momentum situation with a collision, we can always start out by writing the conservation of momentum statement. The initial momentum of object 1 plus the initial momentum of object 2, and if I had 3 or 4 or however many, I'd have each one of those terms, and they would equal the final momentum of object 1 plus the final momentum of object 2. And one of the things, in order to have elastic collisions, you have to have the same number of objects on both sides of the collision. If the number of objects changes, you are going to end up having inelastic collisions. Now, we're also going to assume that the mass of each object has to stay the same during the collision, otherwise there has to be some exchange with internal energy. So, to conserve the kinetic energy, we take our initial kinetic energy of each object, add it together, and that would equal our final kinetic energy of each object added together. So, written out in terms of details, for one dimension, the mass of object 1 times the initial velocity of object 1 plus the mass of object 2 times the initial velocity of object 2 would equal the mass of object 1 times the final velocity of object 1 plus the mass of object 2 times the final velocity of object 2. And for kinetic energy, 1/2 times the mass of object 1 times its initial speed squared plus 1/2 times the mass of object 2 times its initial speed squared equals 1/2 times the mass of object 1 times the final speed of object 1 squared plus 1/2 times the mass of object 2 times its final speed squared. We have two equations to work with. So with elastic collisions, that means we can have two unknowns. And often when we're analyzing collision problems, we have the opportunity to know either the initial or final velocities of our objects, and we know the masses of those two objects. So if we were to start with a known initial velocity and a known mass for our objects through a bit of algebra, you can take those two equations and then solve them for each other to express the final velocities of each object as the final velocity of object 1 is going to be the mass of object 1 times the initial velocity of object 1 plus the mass of object 2 times the initial velocity of object 2 divided by m1 plus m2, so that's our initial momentum, divided by the total mass, minus the mass of 2 divided by m1 plus m2 times the difference in velocity, v1 initial minus v2 initial. And for v2 final, we would have that same leading term, the initial momentum divided by the total mass, but for this one we would add the mass of object 1 divided by m1 plus m2 times that difference in velocity, v1 initial minus v2 initial. So I like writing it this way because there's some nice symmetries. This first piece is the velocity that you would get in a completely inelastic collision. If the objects collide and stick together, the final velocity is the total momentum divided by the total mass. Now, for conserving kinetic energy, there's essentially an exchange that happens between the two objects based primarily on the difference in velocity of those objects and the mass of the other object. The final speed of object 1 depends on the mass of object 2. The final speed of object 2 depends on the mass of object 1. Something else neat that happens. Sometimes when we're analyzing elastic collisions, we further constrain them to say that the second object is going to start at rest. So all of our momentum just comes from the first object. Well, if that's the case, the algebra is a lot easier to go through to solve for the final velocities, but from this framework, if I plug in v2 initial equals 0, well, that term goes away, that term goes away, and that subtraction just becomes v1 initial. Well, here I have m1 minus m2, both times v1 initial, and here I have m1 times v1 initial, m1 times v1 initial. All that survives, if we have an initial velocity of our second object equal to 0, our final velocity of object 1 is the difference in mass, m1 minus m2, divided by the total mass times v1 initial. And for v2 final, it's 2 times the mass of object 1 divided by the total mass times v1 initial. So, if our objects have exactly the same mass, like billiard balls have in elastic collisions with no spin, well, the first object would stop, because m1 equals m2, we get no velocity for object 1, and then 2 times m over 2 times m means the velocity of the second object would have to equal the velocity of the first object. We just take that velocity and transfer it to the second mass. Now, if object 1 is larger than object 2, object 1 keeps going after the collision in the same direction, but object 2 flies away faster than object 1. And if object 2 is more massive than object 1, object 1 will rebound while object 2 moves in the original direction. So an example of that is colliding something with Earth. So if you take a high bounce ball and bounce it off the surface of Earth, well, a high bounce ball has a mass of a few grams. Earth is a lot bigger than that. And basically, a tiny number minus infinity divided by a tiny number plus infinity, well, the limit, as the mass 2 goes to something almost or practically infinitely large, we get -1. So for an elastic collision between a tiny object and a huge object, the tiny object would just rebound with the exact same speed that it had in the exact opposite direction. And Earth, well, 2 times the mass of a bouncy ball divided by the mass of Earth is pretty much 0. So the large object over a single collision with a tiny, tiny object isn't gonna do anything at all. Thanks for watching.